Hi, welcome to our next level 3 differentiation video. One of my favourite topics, we're going to do optimisation problems. We know calculus is used to determine maximum and minimum turning points. We're going to extend that idea to real life applications such as maximum or minimum area or volumes, maybe maximum costs or profits, or maybe we want to minimise things like surface area, waste, or time and staffing. Let's get going. We've got two examples to look at. Example 1, the temperature in Porirua on the 22nd of July 2018 over a 24-hour period was to be modelled by the following function, where small t is time in hours and big T is temperature in degrees Celsius. We need to determine the maximum temperature. Now notice we've been given the function already, so the only thing we need to do is differentiate it to get a gradient rule. We're going to use the quotient rule because it's a function divided by a function, and here's the gradient rule here. We're going to simplify that to get 160 minus 40t squared divided by bracket t squared plus 4 bracket all squared. So this is our gradient rule. Now we're going to put the gradient rule equal to 0 because that's when a maximum or minimum occurs with a 0 gradient. So we're going to solve this equation. Now because it's a fraction equal to 0, we only need to worry about the top part being equal to 0 because we can't have the bottom part equal to 0. So we're going to go 160 minus 40t squared is 0. And we're going to solve this equation. It's a quadratic, so we get two solutions, 2 hours and negative 2 hours. Now, if we ignore the negative 2 and focus on the 2, let's substitute that value 2 back into the temperature function and get a maximum temperature of 20 degrees Celsius. Here's what the function looks like. It's a weird-looking function, and we've worked out that 2 hours after we start time, we have our maximum temperature of 20 degrees Celsius. If I was to extend that on a little bit, the graph, you'd see it carries on in both directions, and you'd see in the negative direction there's a minimum turning point, which is our negative 2 solution. Right, move on to example 2. In New Zealand, a Coca-Cola can has a capacity of 355 mils. We're going to determine the radius of a can that has a volume of 355 centimetres cubed, which has a minimum surface area, because we're trying to minimize the amount of cost and amount of aluminium we use. So we're trying to minimize the surface area. Right, we need to form our own function. We haven't been given that. So here we go. Here's a cylinder. I know it's not as flash as the real Coca-Cola can. We're just going to assume it's a perfect cylinder. Here's a net of what a cylinder looks like, with the radius of the circle is R and the height of the can is H. This base part here, the rectangle bit in the middle, that's the bit that folds around and wraps around, has got a length of 2 pi r, which is the circumference of the circle. That's the bit that wraps around the circle. All right, let's work out the surface area. We've got pi r squared, which is the area of one circle, but we're going to times it by 2 because there are 2 circles in the net. Now we're going to do the rectangle bit in the net, which has a base of 2 pi r and a height of h, so it's 2 pi r times h. Right, this is the formula for the surface area, but the problem is it's got two variables. It's got a variable r and it's also got this variable h. So we're going to replace this variable h, and here's how we do it. We're going to go back and work out the volume of a can, which is pi r squared h. We're going to put that equal to 355, and we're going to divide both sides by pi r squared. Get h is equal to 355 over pi r squared. We're now going to substitute that back into h to get this part. Now we're going to simplify this. The 2 times 355 gives 710. The pi's cancel, and one of the r's cancel on the bottom with one on top. Right, we're going to take this r on the bottom and we're going to bring it up to make it r to the power of negative 1. And this now is our formula for the surface area, and it's only got one variable, which is r. So let's now differentiate it to get this function, 4 pi r minus 710 r to the power of negative 2. Now we can put the gradient rule equal to 0, and I'm not going to go through the rest of the algebra on this video. You're welcome to pause the video and stop it, but we finally get an r value of 3.84 centimeters. I've only just looked at 2 videos, but please go and practice these a lot. Thanks for watching.